Okay, let's go ahead and look at Chapter 9. With Chapter 9, I'm going to review this a little bit differently with you all. I'm going to hit several key things that you should know as shown in key concepts, definitions, and formulas. And then I'm going to talk to you about two specific types of problems you should be able to solve from Chapter 9. And that's to help you streamline a bit your studying for this chapter. Okay, so basically what we're talking about here is inflation, treasury securities, treasury markets, and we have our definitions of inflation and things like that. And I am jumping ahead here on purpose because one thing you should definitely know in this chapter is the relationship between nominal interest rates here. This is the R that we know and love that we have been using all along, and our rate of inflation here and our real rate, which, as you can see for us, the real rate of your investment is your nominal rate minus what's eaten away by inflation. So we do want to keep this in mind and know how to use this. And so that's number one important takeaway from this chapter. Second important takeaway from this chapter is that treasuries are called risk-free, but they do have some risk, right? There are risks in treasuries, and they have risk that is shared with any investment. That's duration risk. The longer treasury you buy, the more interest rate you would expect to get from that, because the farther out you go, the higher probability of a bad outcome there is, even for US government, etc. And then there are also risks here that are specific to treasuries, including inflation, interest rate, and default. So with all this in mind, we call our treasuries risk-free securities, even though we know that they have some risks, and we write our risk-free rate, which is really measured by treasuries, as R risk-free or RRF. Okay, so risk-free risk is going to be an important component of risk for the rest of the term, and it's measured typically by treasuries, but it does include duration risk, inflation, interest rate, and very small default of US government risk. And the third thing that I want to highlight for us in this chapter is the treasury yield curve. And that's a curve like this that is constructed from looking at a bunch of zero coupon treasury bonds that have different maturities and just plotting on a graph, put on the x-axis how many years to maturity, and put on the y-axis for each one their current YTM over here. And as we'd expect during normal conditions, this is, if we draw a line between all the x's, we get an upward sloping curve, and that's because the longer time we want to invest in a treasury security, even though it's pretty low risk, the more interest we want from that. And this shows us very clearly our duration risk for the treasury. So you can look at this curve and say, for a 3-year treasury, what's the approximate interest rate that investors require for that? And at this time 2 here, I'll focus on time 2. At that point, it was about 5%. We could read over to YTM of 5%. Okay, and that is also our RRF on this graph. Okay, so with that, specifically for the exam in Chapter 9, you should be prepared to do these two types of problems. One problem where you're given a bank or somebody offering a deal and you want to find what the real rate of return is, or maybe I'll give you the real rate of return and ask you what inflation was at the time, or give you the real rate of return and inflation and ask you what the nominal rate was, that sort of thing. So this is taken from practice problems. We've got a video up with this exact problem. You can look at the Excel spreadsheet with a solution is also given to you. And the second type of problem you should know from Chapter 9 specifically is the type of problem that illustrates that Treasury securities and risk-free risk in quotes are not risk-free. So this is one of these problems where something changes overnight. And so we're assuming that risk-free risk is equal to inflation plus everything else that's measured in treasuries. And so overnight, so typically in a problem like this, I'll say to you, you've bought a bond like this, and overnight inflation doubles or something. So how much could you sell the bond for? So you've got to be able to go from the RRF when you bought the bond to the RRF the next day with the change of inflation, and then just apply the present value, future value formula to solve for whatever is asked for. So just make sure you can do these two types of problems as illustrated in practice problems for handout 9. And with that, let's leave out the rest of handout 9 and jump into handout 10. So in handout 10, we first distinguished between diversified projects and undiversified projects. So diversified projects have a whole bunch of little similar investments hidden inside them. So for example, if we bought some shares of the SPY ETF, if we just bought one share, we would still have fractional ownership in 500 publicly traded companies. That's diversified. That's a diversified stock investment for sure. An undiversified project is just where we're looking at one thing at a time. We may put a bunch of undiversified projects together in a portfolio to get a diversified portfolio, but when we're looking at just one project at a time, then it's undiversified. So for example, if we decided to buy shares of Salesforce.com in isolation, that would be an undiversified project. If we're working for Lukoil and we're trying to suss out whether or not they should build one new gas station, that would be an undiversified project for Lukoil. And you could consider to throw all of your savings into buying one rental property. That would be a bad idea. But in general, if you're thinking about buying one rental property, that would be, when we're looking at just that one property, an undiversified project. And for undiversified projects in general, we have 4 risks. So duration risk, okay, in all financial projects, and that's measured by T in our discounting equations, right? Okay, and that's measuring the increased probability of a bad outcome with the length of a project. Okay, this here I'd like to note a typo in earlier version. There was an earlier version of these notes posted where I think this said featured in Treasury securities, but risk-free risk is involved in any financial project because the least risky project we can do is a Treasury. So risk-free risk includes that Treasury stuff. So you can't get away from risk-free risk or duration risk no matter what. So what's our risk-free risk? It's our inflation, our interest rates, and our default risk. We usually measure risk-free risk by treasuries, but risk-free risk itself is not the treasury, it's the risk of inflation, interest rates, and default risk of the US government. So the risk is risk-free risk, it includes these components, and it's measured by treasuries. Okay, but it's risk-free risk is not treasury securities, it's measured by treasury securities. Risk-free risk, these 3 things measured by treasury securities. In the same way, duration risk is the increased probability of a bad outcome with the length of the project, and it's measured by T in the discounting equations. Okay, then for general other undiversified projects, we have our increment for industry or market risk. Okay, and this is measuring an industry-wide disruption, bad macroeconomic events, stock market crashes, et cetera. So right now, doing this at the end of March in 2020, the restaurant industry, for example, is experiencing a horrific downturn, really a shutdown. So that would be an example of an industry-wide disruption for the restaurant industry. And that's, of course, been accompanied by a stock market crash and other things. Um, and then also the fourth chunk of risk for undiversified projects is project-specific risk, and this will be all non-diversified projects. And this is what I think of as shorthand as bad manager risk, but it's really this project's unique issues. So, for example, to go back to the restaurant analogy, if we were looking 6 months ago, the restaurant industry was doing very well, but if we had someone who came up with a really bad menu, or in their restaurant they didn't keep their tabletops clean and their silverware looked dirty and stuff like that, that bad management would cause any particular restaurant that we might consider investing in to go bad. And that has nothing to do with the industry, which was very healthy. That would just be a bad management team for this particular restaurant or restaurant chain. Okay, so we want to incorporate all of these risks into our financial models when we're looking at one project at a time, when we're looking at undiversified projects. And we're always, as hopefully you've noticed by now, we're always evaluating these projects using our discounting equations. So using our discounting equations, we have duration risk built right in there by this exponent in the denominator. The longer we go out in time, the bigger the denominator is going to get, which is going to mean the smaller the impact of this cash flow for us is going to be at t equals 0. So that's built in naturally to the model. For the rest of the risks, we have to choose, do we want to put them in the cash flows, or do we want to put them in the interest rates, or some combination? And any model that we have should measure all our risks and not double count our risks. And how the four risks are measured by virtually everyone in the world, actually pretty much everyone in the world but Warren Buffett, who does things slightly differently, works as follows. In the discount rates, everybody in the world but Warren Buffett includes the risk-free risk and an increment for industry or market risk. And in the cash flows, they'll try and put the project-specific risk. And as I've said before, built into our discounting equations, our duration risk is measured by time. So just for out of interest, Warren Buffett discounts with only risk-free risk, and he puts his industry or market risk in the cash flows along with project-specific risk. Again, he really is truly about the only one in the world I know who does that. What I've got for you here really is true for virtually everyone else in the world. Okay, so when we include our risk-free risk or industry risk risk-free risk and industry or market risk in R, we write R as RM, which stands for our market, or ROCC, which stands for our opportunity cost of capital. Okay, and these two are equivalent. They mean exactly the same thing. Depending on what textbook or even what chapter of what textbook you're looking at, you'll see one or the other, but they mean the same thing. They always include risk-free risk and an increment for industry or market risk, okay? And so that means that we're going to put our project-specific risks in our cash flows, okay? And then these cash flows are going to be called project risk-adjusted cash flows. So then we looked at two risk models. The first one was the opportunity investment model, which we'll be using for the rest of the term. So it's kind of important. It's an opportunity cost of capital model, exactly like you might have learned about in macroeconomics. Very similar to what you may have seen. I know it's not a requirement for this class, but those of you who have seen it, you've maybe seen this in your macroecon class. So then we need to know what is our opportunity cost of capital. And all it is really, it's a discount rate that aims to measure our risk-free risk and an increment for market or industry risks. Again, we always write it as ROCC or RM, and it's often called for short cost of capital. So our opportunity cost of capital formally, in terms of a definition we can apply for problems, is it's going to be our known interest rate or discount rate for a diversified set of alternative projects with similar risks as the project we're evaluating. at the moment. So with that in our pocket, let's see how this opportunity investment model works. So the whole idea here, the key, the objective of the model is to find ROCC. So it does it via 3 steps. First, we have to know what's our mission in life as an investor. If we're working in the new gas station division for Lukoil, it could be to find opportunities for profitable gas stations in new Midwestern markets in the US. That would be a good investment mission. Here are a couple others. We invest in short-term securities with strong contractual guarantees. So these would be like one-year treasuries or CDs. A different investment mission could be, this might be for a hedge fund manager. We invest in high-risk, long-term asset-backed securities, which might be things like subprime mortgage-backed securities. So we have to know our investment mission. What's our purpose in life? And once we know that, then we want to find an opportunity cost investment that's compatible with our mission. And remember, our opportunity cost investment is that diversified portfolio of known projects with market or industry risks that fit our investment mission. And once we know that, this is a really great thing, because once we know that, all we have to do is estimate the native R, interest rate or discount rate, for our opportunity cost investment, and that is our opportunity cost of capital. So that's how this model works. We need to know our mission. We need to find an opportunity cost investment compatible with our mission, and then we need to estimate the interest that we'll earn if we invest in that mission, and that's called our opportunity cost of capital. So question comes up, why do we want to specify diversified portfolio here in our opportunity cost investment? Why don't we just say a known project with market risks and risk-free risks that fit our investing mission? Well, the reason is this. This is true for pretty much all of investing. If we look at a graph with the number of projects in our investment portfolio on the x-axis and risk, this would be measured by dollar loss, volatility of gains, etc. So I want to be not very specific about what I mean by risk here. It could be a lot of things. But you notice if we have very few projects in our portfolio, we have a huge amount of risk, and we can cut this literally by about 50% by having when we get to about 30 projects, we're pretty much there. So what we say in finance is that smart investors always invest in a diversified portfolio of projects, because that automatically cuts down our risk. And that leads to the saying in finance that diversification in finance is one true free lunch. So we want to make sure that our opportunity cost investment takes advantage of this benefit of diversification. Okay, so some important properties of our opportunity cost of capital, now that we have it, is the beautiful thing about this model, the opportunity investment method, is that we can make investments with our return of opportunity cost of capital at any time just by adding to our opportunity cost investment position. So this, again, to borrow from what some of you have seen in macroeconomics, maybe even in this case in your micro course here, our opportunity cost of capital is the rate we forego by pursuing a new opportunity instead of putting our money simply in our opportunity cost investment position. So our strategy for analyzing projects becomes, is the interest I'll get in this project bigger than what I would get if I just threw my money into the opportunity cost investment project and earned opportunity cost of capital? Okay. Other thing that's important is the riskier our investment mission, the higher our opportunity cost of capital is going to be. And whenever we're discounting with our opportunity cost of capital, we want to use our project risk adjusted cash flows. Okay, so now the opportunity investment model has given us how to find ROCC. We also want to know how to measure our project-specific risks, and those, of course, are going to be in our cash flows, right? So here's a good method for doing that that works with and really as part of our opportunity investment model. You want to distinguish between two types of flows. Our promised cash flows, these are what's stated in the contract, and they don't include any risk because these are the best case. What's in the contract is what we're going to get if nothing goes wrong, right? This is what we get if nothing goes wrong. So there's no risk in those promised cash flows. What we need to also consider are our expected cash flows. These are expected values, and this is going to include consideration of our project-specific risks. So various scenarios. So say the restaurant does come out with a crummy menu. The restaurant does have bad hygienic stuff. So their tables are dirty, their silverware looks dirty, stuff like that. And for each scenario, we want to see what our future cash flows would look like in our best estimate. This is hard to do. And we also want to consider the probability of each scenario, the probability of a good management team with a good menu and an awesome looking clean restaurant, and the probability of a bad management team with a bad menu and maybe not such a great looking restaurant. So here's an example of how we do this. Let's say we're looking at a bond with a contract requiring a payment of 100 in 1 year. So 100 is the promised contractual flow, and then something that would be given to us is that our general manager or you, after you've gotten your awesome degree from Miami, you could, after a bunch of work, say, well, I believe about 9 times out of 10, a company like this is going to meet its promise and give me the promised cash flows. But about 10% of the time, a company like this is going to make some bad management decisions that will cause them to default. This is not default cause to industry or macroeconomic recession. This is default just to bad management decisions. And I further, after a bunch of work, again, this would be given to us, my estimate would be that we would get in that case that 1 out of 10 times our cash flow 1 would not be the promised cash flow of 100, but it would rather be the cash flow we'd estimate of, say, $50. And the way to think about this is if we buy bonds like this a lot of the time over and over and over again, which is what we will do because it fits our mission, 90% of the times we will get the promised cash flows and 10% of the times we won't. And when we don't, we're going to get 50% of the promised cash flows. So then how we want to use this is we want to say, what's the expected value? So this expected value is just probability of getting the promised flow. So 90% times 100 plus probability of getting the flow if things go bad. So that's 10% times 50. And the weighted average of that is just adding this all up together. And that's 95. And the way to think about this is after we make investments like this many times, after we run a project like this many times, on average, we're going to get 95 per project. And then we closed out this chapter with a look at other risk models. In particular, we really just looked at one called the capital asset pricing model, or CAPM. This is also an opportunity cost of capital model, and it's used almost exclusively for stock investments. And so here's how it works. It says we're going to discount our project risk-adjusted cash flows to an entity's owners. Remember, we're talking about stock here, so we're talking about an entity's owners. Okay, we're going to discount these cash flows with what we're going to call RE, or R equity, in the model, where RE comes from this equation. RE is equal to our risk-free rate plus this thing called beta times our market interest rate minus our risk-free rate. So this is increment for market risk in parentheses. So that's the CAPM model. I've got a lot of details on the CAPM model here that we are going to have to come back to in a future chapter. But for exam 2, you really just need to know that the CAPM model exists. It's an opportunity cost of capital model, and it's used mostly for stocks. So this is really all this page is. So just know that it exists. It's an opportunity cost of capital model, like the opportunity investment model, and it's used mostly for equity stock investments. Okay, and that's it for handout 10. Okay, so let's look at handout 11A. I have to say that 11A is really exciting to me. This is really at the core of what goes on in analytical finance all the time. So we're going to be doing in this chapter, in this handout, evaluation of projects using our discounted cash flow methods or DCF methods or models. So let's jump right in here. And the DCF methods, the great thing about them, as I've indicated before, is that we can use them to evaluate any project. And all we have to do is consider its time normalized cash flows. And what I mean by its time normalized cash flows are simply the present value of its cash flows and the riskiness of the project, which, as we saw in chapter 10, we want to measure in our discount rate and our cash flows. And remember, we have those 4 risks that we always want to consider. We have duration risk, risk-free risk, and then we have an increment for market or industry risk, and we have project-specific risk. So when we talk about DCF methods, we're usually talking about 3 primary methods, and these are the net present value method, the benefit cost ratio, which is also sometimes called the profitability index. I will consistently call it the benefit cost ratio, and the internal rate of return method. For all of these methods, we want to be careful to always evaluate one project at a time for one participant at a time. Don't get 2 projects involved and don't get more than one participant involved in our evaluation. And with our DCF methods, we're going to consider only cash inflows and outflows to and from this project for this participant. So if there's the mother of all big piles of cash in the project and it stays in the project, doesn't flow out to anyone, we don't consider it. We're only considering inflows and outflows of cash, and only to and from the participant's view that we're taking on. And now, happily, we can use a proper sign convention for all of our cash flows in our equations and on cash flow diagrams. So no more of this common sense. We know the PV total has got to be negative in this case because it's an outflow, et cetera, et cetera. For every stinking cash flow for every project, assign it a proper algebraic sign. And then finally, we're going to evaluate all our cash flows at t equals 0. This is what I mean by normalizing them back to t equals 0, because then they're all on an apples to apples basis, and we can do things like add them together and make ratios out of them and stuff like that. So our key assumptions are going to be, for right now, let's look at a participant who's considering independent projects and a participant who has an unlimited budget. Additionally, we're going to have to include all the marketplace and investor assumptions and implications we've already covered. I had a big slide with a whole mess of assumptions we had to consider. So just remember, there's a lot of other assumptions in our models too. And later in the next chapter, we'll look at an alternate set of assumptions here. We'll look at mutually exclusive projects instead of independent projects. And we'll look at having a limited budget, or what's called in finance capital rationing. So let's start with, we're going to walk through our 3 methods here. Let's start with the NPV method. And to do that, we need to have our definition of net present value. And net present value is just the sum of the individually present valued cash flows for this project for this participant, including every stinking cash flow. anything paid or received at any time. So first, what we're going to do is for each cash flow that she hopes to get, she has to put out as a cost in the beginning of the project. We're going to present value each one of those individually, and then we're going to add them up, and that's called the net present value of the project for that participant. So we can write this mathematically, and here's our NPV equation. And it looks very much like our PV tote equation that we had in chapter 8b. The difference here being now is that we're going I is equal to, instead of from 1 for that first future cash flow, I equals 0 to number of cash flows. So this ensures that we capture any cash flow at t equals 0. T sub I is still going to be the time of cash flow I, and CFI is going to be our project risk adjusted cash flow I. So very similar to our PV tote equation, but we're just moving our index start point to 0 to make sure we capture every stinking cash flow. And now, of course, also we're using a proper algebraic sign convention here. So there are two important properties of the NPV formula. The first is that the net present value of opportunity cost investments is equal to 0. And I showed you how that worked in the notes for chapter 11, handout 11. And second is, if we find mission fitting investments, we're looking around, we're looking for projects. If we find one with an NPV that's greater than 0, we should do it, because if we don't do that, we put our money in our opportunity cost investment, we get an NPV of 0. We find something better, we get an NPV of more than 0. That's going to make us wealthier. So this leads us to our rule for applying the NPV formula. We're going to invest in a potential project we're considering if the NPV is greater than 0. And if it's less than or equal to 0, we're not. And what are we going to do with that money? We're going to put it instead into our opportunity cost investment. Nothing wrong with that. That's a good thing to do. Okay, so there are also two important interpretations of the net present value. We looked in the notes at an example where the net present value of a project was $4.76. So I'll continue with that here. So the first interpretation that's important, and we use this all the time, is called the increased wealth concept. And it says that positive NPV projects increase the investor's wealth by the amount of the NPV. So in this case, where the NPV was $4.76, we would say, if we go ahead with that project, if we make this investment, we've just made the firm richer by $4.76. And I showed you how that actually does work. It's true, it's true, it's really true in the lecture for handout 11. Okay, but there are some caveats on this. Richer is not measured against doing nothing. It's measured against putting the money we had for the project into our opportunity cost investment instead, not against doing nothing. Okay, so specifically what I mean is, if we didn't make the investment in this project, we would have put the cash into our opportunity cost investment and enjoyed an NPV of 0. Second important concept is called the equivalence concept, and that says investing in our positive NPV project is completely equivalent to receiving its NPV today. And again, in the lecture for handout 11A, I went over showing you how that is true. Honestly, the increased wealth concept is the one that we use more, so it's important that you understand that one. Okay, so let's move on. Our second DCF evaluation method is the benefit cost ratio, and this is a ratio just like we had in our ratio analysis chapter. So the benefit cost ratio is defined to be, in the numerator, the present value of all the positive cash flows for this participant for this project, divided by the absolute value of the cash outflows. So these would be the negative cash flows, okay? And PV, of course, means we've discounted them all first. And what are we discounting by? We're always discounting by, with these methods, our opportunity cost of capital that we got from our opportunity cost investment. So As always, first present value each cash flow, then add them up. Never, ever, ever add up your cash flows without present valuing them first when you're using DCF methods. Okay, so the BCR method is not quite as good as the NPV method because it doesn't say how much wealthier a project will make us. That's why we think of it as sort of a bang for our buck ratio, but it's more important to know how much wealthier a project is going to make us, and BCR does not help us with that. And our third and final, for us, discounted cash flow evaluation method, we looked at the internal rate of return method, or the IRR method. So first we had to define what we meant by an internal rate of return. And an internal rate of return is just the discount rate or the interest rate that makes the NPV of a project equal to 0, okay? And mathematically, how are we gonna make that work? We're just gonna go back to our NPV equation, and we're just going to set it to 0. So over here, we have on this side exactly the NPV equation as we first developed it, except instead of putting our opportunity cost of capital in here, interest rate, discount rate in here, we put in the internal rate of return, and now we solve this for the IRR. Okay, so that's the idea with the internal rate of return DCF evaluation method. So how are we going to use this method? Well, as always, same with all DCF methods, we want to establish our opportunity cost of capital and all our cash flows, and then we'll solve for the IRR using these cash flows. And now we're going to compare the internal rate of return to our opportunity cost of capital. If the internal rate of return is greater than our opportunity cost of capital, what that means is our cash is going to be growing faster than our opportunity cost of capital rate of growth, so we should go ahead. On the other hand, if our internal rate of return is less than our opportunity cost of capital, what it means is that our cash would be growing in this project at a slower rate than it would be growing in our opportunity cost investment. So we don't want to go ahead. We'd want to put our cash into our opportunity cost investment instead. So the IRR method has a couple of problems. It has problem number 1, which is same as the BCR method. Okay, it does not tell us how much wealthier a given project is going to make us. Okay, same as BCR, but it's got another problem, which is actually much bigger. And that's that when we're solving this means always when we're solving something like this equals 0, we're finding the roots of a polynomial or a real equation. And as I showed in the lecture, for complicated examples, we might have a complex number solution for the roots, and we might get a bunch of roots, and we don't know which one is correct. And neither NPV nor BCR have this problem. So we would say, in the quants in finance would say these are more robust methods than the IRR method. However, we have some good news here. Math to the rescue. People way much smarter than me have found that the IRR method is guaranteed to work for 4 types of projects. Something like this where you have a negative cash flow only at t equals 0, all the other cash flows are positive, or if you flipped this thing over the x-axis and you would have 1 positive cash flow here and all the rest negative. Or on the other hand, if we have all negative cash flows here and 1 positive one at the end, or we could flip this over the x-axis and we'd have all positive cash flows instead of 1 and then 1 negative one at the very end. For these 4 cases, the 2 that are shown and the 2 additional we get by flipping these over the x-axis, the mathematicians have shown that the correct IRR is the smallest real positive root of the polynomial equation, or the real equation. The IRR method is not guaranteed to work for projects like this, where you may have a positive or negative cash flow at any old time. So the good news is that projects like bond projects, for example, are perfect for the IRR method because they always look something like this. And usually they have a bunch of uniform cash flows and then one big blobby cash flow at the very end. Or they might look something like this. So these are the IRR method is great for bond projects, and the yield to maturity is the IRR for the project by the bond, evaluating with non-risk adjusted cash flows. And also the IRR is very appropriate for loans, where we saw for mortgage loans, we typically get a big blob of money in return for making a uniform payment back for 3 years or 30 years, whatever it is. So IRR is used for projects like these all the time. It works just fine for them. Okay, so now in terms of you solving IRR problems in homeworks and on exams and things like that. So for a 2 cash flow project, you can always find the IRR with algebra and a calculator, right? You just go back to the FV is equal to PV times, you know the story, 1 plus R. We could say IRR raised to the T, something like that, and you can do the algebra and solve for the IRR. Okay, if we have a 3 cash flow project where cash flow 1 occurs at t equal 1, cash flow 2 occurs at t equal 2, and cash flow 0, of course, happens at t equals 0, we can find the IRR with the quadratic equation. So for a 3 cash flow project, where the cash flows happen at integer times, like end of year 1, end of year 2, not end of year 1.5, end of year 2.7, or time 2.7. If we have something like that, we'll get an equation that looks like this, and we can multiply both sides by 1 plus IRR squared. And that's going to give us, when we do that, an equation that looks like this. And all of us hopefully will recognize this as something we were tortured with in high school or grammar school, depending on your education. This is our classic find the roots of a quadratic equation, a parabolic equation, and whoops. And this is exactly, this up here is exactly of this form, 0 equals ax squared plus bx plus c, where in our case, x is equal to 1 plus IRR, a is equal to CF0, b equals CF1, c equals CF2, and then IRR equals x minus 1. So we can solve this using the quadratic equation, and I did an example showing how to do this, I think, in one of the example practice problems. Okay, and I think that is it for this handout 11A. So let's move on now to handout 11B. Okay, so handout 11B had a small number of topics, basically 3 topics in it. The first one is mutually exclusive projects. So remember, I did promise you in 11A that we would soon look at different assumptions other than independent projects. We're doing that now in 11B. We're looking at mutually exclusive projects. We're going to look at limited budget projects. So mutually exclusive just means that if we go for it with project A, we can't do project B. So when that's true, we say A and B are mutually exclusive. The analysis of mutually exclusive projects can get fairly hairy, but there is one class that we can handle really well, and these are called mutually exclusive equal length projects. So these are projects that have to start at the same time, i.e. t equals 0, and they involve cash flows going on for the same number of years. They don't have to all have, if we have a 5-year project, both projects don't have a cash flow, have to have a cash flow at end of year 1, end of year 2, etc., all the way up to end of year 5. They just have to start at t equals 0, and their last cash flow has to be at end of year 5 if it's a 5-year project. So given project, and on the exam, I will not be sneaky with you and give you like a 4-year project and a 5-year project and have to realize, oh, that's not equal length, and it screws the whole thing up, that sort of thing. I'll try to keep it straightforward. Okay, so we want to know, we're going to be using mutually exclusive equal length projects for the purpose of figuring out which one is best. And the answer is always going to be the project with the bigger NPV. And this is going to be a recurring theme. We saw in the last chapter that NPV was really the most robust, most useful method. And we're going to find in this chapter that the one method, the one DCF method you can always count on to give the right answer is NPV. So for mutually exclusive methods, how do we find out which project is best? The one with the biggest NPV. And I showed in the class notes that BCR and IRR may give you the wrong answers. And the reason for that is neither one of these methods considers the scale of the projects. And because of that, they can't say which project will make us richest. Okay, then the second thing that we looked at in this chapter was the payback period evaluation method. And the first thing you got to know about that is that it's not a DCF method. Even though it's in a chapter with discounted cash flow methods, it's not a discounted cash flow method. How does it work? It just says if you're comparing projects, the best one is the one that recovers your costs quickest. So they don't need to be equal length projects, the ones that we're comparing. And in general, we want to use our MEL method or another NPV-based method. But it's okay to use the payback period method for a lot of situations that startups run into. And that would be, for example, when we want the quickest payback for our project. We want to repay our costs at t equals 0 as quickly as possible. Because why? Because we might go bankrupt if we pursue a project with a longer payback period. So this happens in real estate construction all the time. For example, you get a construction loan that comes due in a year. So if your development project is not up and running and generating revenue in a year, you're dead because you can't pay back your construction loan or convert it to a mortgage loan or something like that. So you may be looking at a 5-year project. It's huge, it's wonderful, it's going to make you billions, but you don't start collecting any rent for 4 years, and your construction loan is due at the end of 1 or 2 years, you're going to go bankrupt. So the payback method is good in situations like this. And then the last thing we looked at in this chapter is project evaluation under capital rationing. So first of all, what's capital rationing? And capital rationing is just deciding which projects we want to pursue when we have a budget, right? When we have a budget. And for us, we're considering all projects are going to be independent. So we're back to independent projects now under capital rationing, and no fractional projects. So either we launch the new project or we don't. We do this development of 5 buildings, or we don't do fractional projects. Okay. And how do we decide which projects to pursue? You know the answer by now. It's going to be by using the NPV method. We're going to pursue the set of projects that maximizes the increase in the firm's wealth, which is, of course, maximizes our total NPV without going over budget. And it's really that simple. It gets a little complicated checking all the possibilities if we have a portfolio of 4 or 5 or 6 projects. But conceptually, it's really this simple. We just find the set of projects that maximizes the increase in our wealth without going over budget. And again, IRR and BCR can give wrong answers. Okay, and that's it, and that ends our review for exam 2. So I wish you all well, and I look forward to speaking to you again soon.